So last lesson, whether you were here in person or in spirit, we were looking at differential equations. These are these equations where we're basically undoing differentiation. And in some cases, we get questions like question 2, part A. Question 2, part A is a differential equation. But it's good news, isn't it? Because we are differentiating with respect to x, and the only variable in that expression is x. So if you remember, that makes me happy. So solving that differential equation just requires me to integrate. And I wish I knew how to integrate that. Oh, hang on a minute. Well, if I was asked to integrate that, the answer would be cos cubed x. So it must be minus a third. Cos cubed x plus c, which if you remember we call a general solution. And then, and we're not going to do this one, but you may feel you want to at home, we would substitute our values in. Y is 0, x is pi over 3, remembering that whenever we're integrating or differentiating trig, we need to be in radians, and we'd then work out c, and that would give us our particular solution. So particular solution, no constant, we just substitute a pair of values in to work out the value of the constant. However, the vast majority of differential equation questions that we meet are not like that. They are more like D here in question 1, where x is our variable, but we've got both x and y. And this was the technique that we focused on Friday, and I wanted to start by going through that one because it throws up quite an interesting conundrum. If you remember, we use a process called separating variables, where we collect everything with a y on one side and everything with an x on another side, including the dy and the dx. But the problem we've got here is that the x and the y are trapped within the power of e. So the first thing we need to realise is that that question can be rewritten as because when I divide powers of the same thing, I subtract the indices. So go on, now just see if you can, and if you were here and you'd already done this question, then I've given out the book so you can work through, but can I get you to do what we were doing last lesson and separate those two variables for me? Can I go at that one? So we want the dx, I've multiplied both sides by dx, so we've got dx on the left hand side, and I want everything with an x on that side, and then the dy has stayed where it was, and I want everything with a y on that side. Hopefully you multiplied both sides by e to the y, which gave us this. And compared with some of the ones that we have to do, this is quite nice because we get, when you integrate e to the y with respect to y, it stays as e to the y. And when you integrate e to the x, you get e to the x, and the 2 passes through unchanged. We get a constant here, and we get a constant here. And as I said on Friday, we just write that as a single constant. And sometimes we write that as an ln of some constant, just because it means we can combine it with other logs. no such luck in this case, but I am now going to, because the question wants the answer written in y equals form, I'm going to undo e to the power of, which I do by lning both sides. So that gives me, and there's no nicer way of writing this, sadly. So I have two variables, x and y. I separate them and I do it as two separate integration sums. I write a single constant, and if it just wants a general solution, my work is done. If it had asked for a particular solution, I'd be looking for a pair of values to substitute in. Yes?
Why do you only put the c on one side?
Because if I've got a constant here
Yeah.
and a constant here, I could take that constant away from both sides, which will just give me a different constant here. So we just write it on both sides. We know there's potentially some number here and potentially some number here, so that is the combined. Yeah. Okay, can I get you to open your books at page 324, 325? We're going to work through question 3 now, but a number of you who are here or have watched the video or are up to speed already may want to jump ahead. So I'll give you a minute to have a look at that question. So some of you are ahead of me, you just keep working independently. Some of you tune in and make sure you're listening. In order to separate the variables, I need my x terms and my y terms to be separate. A bit like we did a moment ago with that e to the x minus y. We wrote it as e to the x over e to y. I've got to do the same here because I've got this sort of mixture of x and y here. I think there's actually a little note in the textbook, isn't there, that gives the game away. I firstly want to do that. And that then allows me to separate my variables. So I've got all the y's on this side and all the x's on that side. Again, I'll just give you a second to see if you can puzzle that one out. This is quite a nice question because of what the x ends up as. Okay, so I get to here. Now on the left-hand side, I'm okay. I know that 1 over y, with respect to y, is going to become ln of y. This doesn't look like something I've come across before. However, two things divided by one thing, I can write as two separate fractions. I can't do that the other way around, can I? One thing over two things, I can't. But I can write this as 1 over x squared plus x over x squared. One over x squared, in order to integrate that, I have to write it as x to the power of minus 2 and just do my normal increase the power by 1, divide by the new power. This cancels out to 1 over x, which becomes a log. 1 over x becomes ln of x. So just see if you can write down what you get. It's not pretty. It's not pretty. You know, I'm not pretending otherwise. Okay, 1 over y becomes ln of y, remembering you need the modulus signs, although actually they disappear in a minute. X to the minus 2, increase the power by 1, so it becomes x to the minus 1, divide by the new power. 1 over x becomes ln of x, and then there's a constant. And actually I could leave that constant as plus c, but we actually found that rewriting that as the log of something, you know, this is a constant, that's a constant. It just means that I can combine things a little bit more easily and write this term as, actually no, I'm going to leave it like that. You'll see why in just a minute. So that is a general solution. That is a final answer. It's just the question, I believe I'm right in saying, wants it in the form y equals. So I've got to undo ln'ing this time, which is by taking e to the power of both sides. That means I get this rather horrible looking answer. The reason I've chosen to do this question with you is because of the next step. This is a little bit like that e to the x minus k, one we did a moment ago. This here can be rewritten like this. Because when you multiply powers of the same thing, you add the indices. Now, why have I bothered doing that? Well, E and ln are inverse operations. So, e to the ln of x is x, and e to the ln of k is just k. So I end up with where k is my constant. I've just got a value to substitute in now. That's a general solution. They tell me in the question about that pair of values, so see if you can just turn that into a particular solution for me by substituting that value in. So actually that falls out quite nicely, because you end up with, this becomes 1, minus 1 over minus 1 is 1. This becomes minus k, and they're multiplied, so you get minus that. Divide both sides by e to the power of 1, and then divide by minus 1. So my final answer is and I need a minus in there as well, so I'm going to put that minus at the front. Have I done that right? So P. I think so. I'll just check to see how they wrote it themselves. Absolutely right, thank you. Oh, they've combined it 3x. Oh, no, that's what we got, isn't it? Yeah, that's what we got. So they just put the two powers together, but there's no need to do that. Now, I've realised that if you haven't watched the video, we've jumped in really, really steeply there. The video, we certainly start a little bit easier. And please make a note of these numbers. It may well be that we have a bit of time this afternoon to do that, but I want to try and get through as much of the theory this morning as we can. So rather than spending the rest of this lesson just practicing that, I want to move on, because the vast majority of questions that we do are of a particular type. They are modelling questions. And I think it's 2 L's, but so I want to talk about modelling with differential equations, which will give us plenty of practice of what we're doing here. So it's not like I'm moving on quickly before giving you any chance to practice. We're talking about modelling with differential equations. And by that I mean practical, although sometimes they're somewhat contrived, examples where we start with a differential equation. Because don't forget, dy by dx is telling us the rate at which something is changing. And particularly if it was d something by dt, that would be the rate it was changing over time. I would propose that we are going to encounter 2 sorts of problems. This is the first type. In this type, we are given the equation. And if you've watched the video, you know we do actually have a way of approaching this by flipping it over. I'm not going to do that. I'm going to use, because I think actually the separating variables approach is a little bit easier, and it's only one thing rather than learning 2 different things. So leave the 3 where it is, move the p to give me a separated variable differential equation. Leave the 3 where it is. Okay? So here we're told about the rate of change. We're told it's an increase. So we know this is a positive dp by dt, which means p is positive. Actually, it doesn't tell us that. It says the rate of increase, so I guess p could be negative, in which case it would be a decrease. So we were given a differential equation. Notice there's no mention of differential equations in the question, so we had to recognise it as such. And solving it means undoing the differentiation. So I'm going to integrate both sides. This becomes the ln of p. I was hoping I could dispense with the modular signs, but I'm just going to be a little bit more careful. And on this side I've just got 3, which if you integrate 3 with respect to t, it gives you 3t. Plus a constant. I'm umming and ahhing at the moment about whether to write c as ln of k. I'm not going to, but I've got that option of doing it. Instead, I'm going to undo the logging by doing e to the power of both sides, and I know therefore that what I've got here is that, which it might be that that's okay, but that's the same as that, isn't it? Now they don't want any constants. They don't use the phrase particular solution, but they don't want any constants. So we're looking for a pair of values. Can we see a pair of values? Sure.
0 and 8.
Yes. This key word here, initially. Always look out for that word. What that means is that when t was 0, p was 8. So go on, see if you can substitute that in and answer part A. You may feel you can go on and do the rest of the question. Please do. Now at this point you might be saying, yeah, I already knew A was 8 because I recognised that this is the expression we often use to describe exponential growth, and when we do, that's always the starting value. So, and my apologies if you'd already spotted that, but it's reassuring that the integration method brings us to the same point. And then finishing this question is just doing stuff that we should already be able to do. So I'll perhaps give you a couple of minutes to see if you can get anywhere with that. So find the size of the population when t was 2, so we just make t equal to 2. Find the time when the population will be 1,000 times the starting value, so we make p equal to 8,000. Divide by 8 and then ln both sides to get 3t equals. And then there's one of those frustrating questions about t. Give you a minute to have a go at that. Okay, so we get 3,200. Just checking that. Yep, 3,200 for that. Sorry, yes, it is B, isn't it? That's right. And then 1,000 times its starting value would be 8,000. So divide by 1,000 and ln both sides, that's how we undo e, divide by 3. Make sure you're careful typing that in. It's not the ln of 1,000 over 3, it's the ln of 1,000 divided by 3. It was a vague question. 2.3 hours was fine. And then that frustrating thing about, you know, the limitation of models is always at the extreme end, isn't it? And in this case, I'm not a biologist, but I would assume that these microorganisms would eventually run out of space or food or whatever it is that would limit them, or they'd run out of space if it was in a petri dish or, you know, whatever. Okay, now forgive me for going sort of breakneck speed through this, but I think if we can get through the sort of the different types, then we can you know, do some practice later. So for the second type, I'm actually switching to a textbook that you haven't got a copy of. My apologies for that. So I'm just pulling that up. Sorry, you should have had that ready. Page 241. Okay, so here is type 2 in this modelling with differential equations section. Type 2 is where no equation is given. And so these questions are all questions where we're told about the rate at which something is changing, and we're asked to write a differential equation. Interestingly, we're not asked to solve it. So this, you know, if this was part A of a question, and it just says, show this as a differential equation, we're not being asked to do any sort of integration at all, no separating of variables. This takes us back to GCSE. So the number of fleas on a cat is increasing over time. That's dn by dt. dn by dt. Now, as a convention, even though whatever we write next could be positive or negative, if it's something that is increasing, we leave it as just positive. But when we come to something that's decreasing, we will write it as negative. We'll come to that in a minute. So dn by dt is directly proportional to the number of fleas. So that means it's equal to some multiplier times the number of fleas. That is the answer to question 1. That is the answer to question 1. I mean, you won't get a question that stops there. It would obviously go on. But if it says, show this as a differential equation, that is the answer. So just see if you can write me a differential equation for 2, 3, and 4. Okay, so with number 2, the value of a house is increasing over time at a rate inversely proportional to the square of x. So the square inversely proportional to x squared means 1 over x squared, and it's equal to some multiple times that, which we could write like that, but we might choose just to write it like that. K is a constant, remember, so you know, that's just a number like 3 or 4. K is just a constant. dA by dt, this is depreciation, it's going down, so we would put minus k square root of a. Okay, the minus indicates this is something that's going down. So we don't just say, well, k will be a negative constant, we say we're going to put a minus there. And then this last one, I guess there are 2 ways you could write this. The rate of decrease of population, so it's negative, is directly proportional to the difference between the population, y, and some constant. So that would be, or other way around. Now, questions like this present us with a little bit of a problem. Let's look at question 1, for example. Let's say we want to solve that differential equation. So I choose to separate the variables. Like we did with that 3 in a previous question, I'm going to leave the k where it is, and one over n becomes the ln of n, k becomes kt, and I've got a constant. There's 2 constants here. So you've just got to be careful with your letters. Don't try and make sure you realise that you've got 2 different constants. This is the multiplier, the constant of proportionality, whereas this is our integration constant. And we've just got to make sure whatever letters you use, they're not the same. Just see if you can do the same for number 2 for me, please. Just briefly, just check you can do the same for number 2. Just get us to this point here, just so we're clear on that. And, you know, we could multiply by 3 and cube root both sides if we wanted to get it in terms of x equals, but that's the thing. Which presents us with an issue if they want us to give a particular solution. We've got 2 missing values. And so in questions like this, you should find you are given 2 pairs of values to substitute in. Okay? Let's have a look at an example of this question. I know we didn't do any examples of the first sort, and you know, I'm trying to reflect the frequency of questions in exams. So here is an example of a question like this. This is actually from your book. Have a go at this one. So actually, it's a coincidence that we've ended up with one exactly the same. Is it increasing? Yes, it is. So actually, yeah, this was not planned, but we've sort of broken the back of that one by what we've done already. I should pretend it was planned, shouldn't I? If this is all planned. I'll just point out one thing. First thing I'm going to do is multiply by 3, which would give me that. Actually, 3 times a constant is still a constant, so you could just leave it like that. Now, I don't know if that's too confusing, in which case leave it as 3c. I'm going to leave it as 3c, but you know, it's still another constant, so you know, it doesn't really matter, but then we get x is the cube root of that. I'm hoping in the question you can find 2 pairs of values to substitute in. 2x equals t equals. I can't help noticing that word initially features again. Oh, why have I got 7 over 16, not 7 over 20?
Because you times it by 3, and then it works out 5. It's something back into it because you.
Oh, because it's
Yeah.
fantastic. Thanks, Callum. Thank you.
Callum pointed me in the right direction.
Yeah, it's interesting, isn't it? In both cases, we've got So when I substitute my first pair of values in, I got that 3c was 1. I wasn't bothered about the value of c because here I've got 3c. So at that point, rather than trying to do it as simultaneous equations, I rewrote my equation, replacing 3c with 1. Now I've worked out that k is 7 over 60, so 3k, thank you to Callum Harrison, whoever it was, is this, as required. Can I just add one thing that I should have mentioned? At the beginning of the question, when you write this, you need to say what your variables are. So we start with that, where x equals the thickness of the ice with units. So it's in centimetres, because there's no mention of units here. The only mention of units is the days thing, and t equals days. Very important in these type 2 questions where no equation is given that you mention your units at the start when you write your differential equation. If you were ahead of me, then the final answer is that